Good evening. I'm Katunja Brendan, your group 22. We're doing graph-based registration for unsupervised East Coast fever detection. We're going to start with the background in the introduction. Basically, the East Coast fever, which we are working with, is spread by the ticks and also by the Cape buffaloes among the cattle in Uganda. So the cattle farmers in Uganda face the challenge of identifying potential outbreaks of the disease early enough in their cattle, as it is very essential for its management and control. So thereby designing a machine learning model for early detection of East Coast fever by providing real-time predictions and actionable recommendations to farmers to reduce the associated risks such as mortality rates can be a high solution that can be actually utilized by the farmers. So the related works and recent trends are used technically. We used graph-based registration and also we used graph attention mechanisms. So the recent trends is that the graph attention mechanisms include the integration of multiple model data, where the modern GAT models are increasingly incorporating the diverse data types such as imaging and non-imaging information to capture a comprehensive view of the disease states. And also another one is that there is enhanced interoperability, where recent models emphasize interoperability by identifying key features and relationships that contribute to the disease prediction. So to give examples, in the study of multiple GAT model that was employed to predict the disease state from the single cell data, achieving high accuracy and providing insights into important cell types and genes associated with the disease. So to compare with our data set, we can see that we have the genotypes that we are actually comparing in predicting this disease spread. The problem statements start with the application domain problem. Cattle keepers in Uganda face the challenge of identifying potential outbreaks, as earlier stated. So identifying it early enough is very essential for its management, as well as controlling the tick infections that contribute its spread. Some of the symptoms of the East Coast fever include the swollen lymph nodes, difficulty in breathing, drop in milk and meat production. There is loss of appetite. So existing solutions are not efficient for the early detection. That's why we have to come up with this machine learning model. I'll talk about the computational problems. One of them is that the data set used to train the model may not be consistent and accurate while relating to some parts of the area, as it was obtained from particular areas, and also imbalanced classes could lead to biased predictions, especially for the disease-resistant cattle, and are represented in the data set. So we had to discard some of the extra classes to come up with a balanced data set which reduces data and makes the model somehow inaccurate. The registration is also necessary to create lightweight model suitable for mobile deployment, but compressing it to come up with a student model makes it less accurate, which also becomes a challenge in predicting accuracy. So the research questions and objectives is that to develop the model for accurate early East Coast fever detection, to develop the cost-effective model that reduces reliance on expensive laboratory tests, to enhance rapid diagnosis, which provides results in minutes instead of days, and also to provide a scalable model that can be employed in rural remote areas via mobile apps and web applications. So the contributions are that we develop the machine learning model to accurately predict the presence and absence of East Coast fever in particular location. We also developed the first machine learning model in Uganda that reduces reliance on expensive laboratory tests, as our API can be integrated via mobile applications. We also develop a scalable model that can be deployed in remote areas. And lastly, we developed a machine learning model that enhances disease tracking through monitoring and mapping of the disease spread. So this is the methodology and system architecture. We have the data sources, dataset, which comprises of the genotype, also temperature, this is environmental data, and then the geographical data. We did data processing, which includes normalization. We also did training of models of the graphical neural networks. We also did unsupervised and also registration. We did prediction and deployment of the model via various platforms, including Render and Streamlit. So the dataset description, dataset used was from Dryad Open Publishing Platform. It contained some missing values and alphabetic values for unbalanced ECF classes. So in the end, we managed to come up with a balanced dataset, as it is shown here for the ECF class, which has ecobars, and also this is the heat map of the features, how they are correlating, and also the genotype classes. We can see that genotype 1 is actually less compared to genotype 0. So these are the output results for some of the models who considered accuracy, precision, recall, and F1 majorly among most of the models. These are the student and teacher models, the confusion matrix, and also the scatter plot for the student model for farming clustering. These are the results we obtained from different models for GNN and student class, and also these ones for the GAT and unsupervised, and also GAT and DCN. We managed to realize that the unsupervised and KD was actually the highest performing model, which we managed to deploy as it has the higher accuracy compared to the rest of the models. Let me invite my colleagues.
Good evening, my name is Bainom Shaderic, and I'll be taking you through the explainable AI results and discussions. And explainable AI is basically to get us to know why the model made certain decisions. And these are some of the visualizations we got from one of our best performing models. While we have on the extreme left, we have a bar chart showing random forest feature importance, and it is useful to discover which environmental factors have the strongest influence on the ECF and the East Coast fever occurrence. And on the left, but up, we have we have line graphs which are partial dependence plots, and and for Cape tick, Kato, and Bio5, and these ones are crucial for understanding how each feature independently affects the probability of East Coast fever occurrence. And then for the local explanation for ECF, it is a sharp plot showing local feature explanation for a classification model for a class East Coast fever. And then we also have XAI results for the one of our worst models, which is the graph convolutional networks model. And if we talk about a few of the graphs which are demonstrating the results of XAI, on the top left, we have it is a bar chart showing random forest feature importance, and it is useful to discover which environmental factors have the strongest influence on ECF occurrence. And the bottom left, we have a permutation importance plot, which is used to understand which features contribute most to the model's predictive power. And if I talk about the model selection, we made a choice of the hybrid model, which consists of unsupervised learning and supervised learning plus knowledge distillation, and it consists of two key elements. The first one is k-means clustering, which enhances the value of clustering information to node features, and graph convolutional networks, which establishes relationships between farms. And furthermore, we also included node distillation to make the model smaller and computationally efficient. And these are one of the results. Some of the results. These are all the results for the hybrid model, which include accuracy, precision, recall, and F1 score, as we see here. And for the deployment pipeline, we had code development where the app was developed using Python, and the code was committed to GitHub on the ECF branch, and then Render cloned the repository, which was on the ECF branch, from the ECF branch, and then Render also installed all the necessary dependencies through this command pip install r requirements, and then Render started the app with Streamlit to run on port 10,000. And for the system architecture visualization, we have the farmer interface where the farmer accesses the app via a browser, and Streamlit handles the user inputs and displays predictions and provides educational resources. And for the backend logic, the utils.py contains load models and the teacher and student graph neural networks, which are useful for predictions. And we also see the models which include the teacher GNN path, student GNN.path, k-means cluster job lib, and these ones it is this that the utils.py loads to, so that it can make the right prediction. And for the storage, we stored our code on GitHub and we deployed it on Render. So this is we shall run through a simple demonstration of the product, but this is the interface of the model, and this is the link. And the potential IP assets, we have graph-based knowledge distillation algorithm, data processing framework, and a diagnostic decision system. And in conclusion, we say that incorporating a hybrid model, it signifies a great step in farm risk classification, and given the use of k-means clustering to enhance node features and capturing of spatial dependencies by GNNs, the model suggests a steady platform to classify high-risk farms. And given that we are also using merge distillation, it further smoothens the process by deploying a lightweight seeded model without compromising efficiency. And for the limitations, we faced a problem of limited computing power, and the potential solution to that is using cloud-based platforms like Google Colab or Amazon AWS. And another challenge we have the first challenge is model deployment, whereby one of the cloud providers had limited computational resources, and we opted to use other platforms like Render. We also had difficulty in finding a data set, so we decided to we had an option to also collaborate with local veterinary institutions and research bodies in order to have correct and accurate information about farm data. We also had problems of memory constraints on the free tier for hosting provided by Render, and in future we opt to upgrade to a paid Render plan for more resources. And for the next steps, we plan on improving the model in terms of scalability and computational efficiency. We also plan to generalize generalize across geographical boundaries and between farming systems in the future, and this could quite possibly result in different performance levels between regions, basing maybe if this is Gulu, it has this kind of ECF density. And then we also have talk about using the hybrid model and integrate it into several systems, and also finding a better data set which has more real world cattle health data sets. And we would like to extend our appreciation to Dryad Digital Repository for providing an unrestricted access to the dataset, and also like to extend special thanks to the original authors of the dataset for their efforts in the data collection. So that was it from us. Thank you very much.